Hi, I'm going to talk about the normal distribution today. The normal distribution is a model for, it's also a function, but it's a model for how to look at data that's natural. Oftentimes, not all natural data is probably with the normal distribution, but a lot of data follows this pattern here with the normal distribution, such that you can have a standard deviation that can basically categorize what percentile data is in based upon where it is relative to the average if you know the standard deviation. And as we talked about in the last video, the standard deviation can be calculated by taking each value, subtracting the average, squaring it, adding all those values together, and then dividing by the number of measurements taken that you did that with, and then taking the square root of that whole value that you got afterwards. And that gives you the standard deviation. So that shows the power of the standard deviation, because you can start figuring things out with the percentile. And I'll get into that in a little bit. So I want to start out with the key here. So I don't know how well you can see the colors, but this is blue. So whenever you see a blue X with a subscript anywhere in here, that is just looking at individual points. So down here, I'm showing how to calculate the standard deviation, which I went over before, and I did it a little bit shorter hand this time using the uppercase sigma character, which is for usually used in Raman sums when you're summing a bunch of basically expressions for each measurement or each value in a series of values. And in this case, that would just be your data points. So whenever you see the uppercase sigma in purple parentheses, whatever's in those purple parentheses is the actual expression that you're using each individual value for, and then you're adding those each time you do the expression for each of them, whatever operation that is. In this case, that's taking each value and subtracting the average, like I just said, and squaring it, and you're adding all those together. Then you're dividing by n, and I put the range here, which would be 1 to n being your last sample, because that's the number of samples if you're numbering each one of them. So whenever you see that, that's what that means. Whenever you see this, that's what that means. Whenever you see an X with a line over it, that means the average or the mean value, which you can calculate. If we were going to use this symbol here, we would just say E and then parentheses. Actually, I'll write it down. It's not going to be purple. Actually, I can make it purple. Give me a sec. So to find the average, we would do this. It's good to start to learn how to format things and look at the symbols. So in this case, we would use a blue X. And then put an I there. And then that's equal to the average. So that's how you find the average there. This one. So whenever you see a green sideways, looks like a 6, I guess, that's a lowercase sigma, and that is the standard deviation. Whenever you see that, what I just talked about here is actually the standard deviation there to calculate that, which is a measure of the distance of points given how much they deviate. You can figure out a value that you can plug in and use here to estimate the percentiles and whatever the actual size of something would be, or the number of something in a trial, for example. And we'll get into how to actually use the binomial distribution to test a binomial distribution to see if that makes any sense. If data is given, like a given purported probability. I showed you one example where you rolled 10 dice, where you rolled 15 times one die, and then you got 10 sixes. That was only with 15, and I'm not sure that that would actually pass in statistics, but it gives you a rough idea of how you can use these kinds of formulas to figure out whether something's believable or not. And it was like 2 and like 100,000 to get that, which makes it really unlikely. But we're going to get more into ways to actually test things, like officially. So, but I want to lay the groundwork foundationally on how to do that. So, whenever you see a P with something inside of the parentheses, that's the probability of something. So we do this here as exercises to understand how the normal distribution works and how it's laid out and how it's mapped, and then also give an example here of how to determine the percentile rank of certain sizes, or in this case lengths. Whenever you see a red Z, Z represents the distance of any point. If you just pick a point, let's say you pick a point here, for example, or like a point on the other side here, and you want to know what distance in standard deviations it is from the mean, the average, that's what Z is. It's how many standard deviations away it is. And I'll get into that in a little bit. So this, what you're looking at here, is actually a plot of the standard normal distribution. And what that means is this is laid out in standard deviations. And a standard deviation, if you go from -1 standard deviation to 1 standard deviation plus positive, that is 68% of this. What we're really looking at here is area. We don't really care about the height of this unless you're using integration to find the area of under this curve. That's actually how you find the probability. As long as the area under the curve equals 1 and it's standardized that way, which the standard normal distribution formula is this way. All the red area that you see under here, if you add it all up, all that area equals 1. Now, I didn't actually give you a y-axis to figure that out, but just trust me, if you use a formula like this, this is actually the plot of this. It's taking Euler's number and it's raising it to the z, and the z is whatever point you're looking at on this. You're raising e to that number, you're dividing by 2, and you're squaring that value in the exponent before you actually do the exponent on this. And then you're dividing by the square root of 2 times pi. Why it's that way, I'm not sure. I looked at it a little bit. It looks like maybe you could look at it as 2 circles for the area, and then z squared, e to the negative z squared. If the average is 0, which it is in the standard normal distribution. So I'll show you this. Actually, this formula will help you. Actually, if you plug this formula in, you can make it so you're actually looking at real values instead of just standard deviations. But for now, like, I've just kept it simple, because usually you just use a table of distribution values with the z value. You find it in the table and you can figure out the probability. There's actually an internet website, which I have on here, that already has that. So if I unlock this, it can show you, like, if you move your finger along, you can see, like, you can actually see the percent probability of some point being wherever the end of that ends. And you can also adjust it. If you scroll up, you can adjust it to 0 to z, or up to z, or z onwards, which would just be the right part. And you can actually look at the actual percent probability. So in this case, this would actually be, if you're just using probability, which actually isn't a percent, it would be 0.3936 is your probability, which is just over a third, almost 40% Pretty nifty tool. You can go to mathisfun.com data or /data/standard normal distribution table, and you can find this. This is really, really useful. Now, I haven't used the exact numbers. This is actually kind of what my textbook shows. And it's easier to remember these values than these, but it's hardly any different. And we're going to use these values in these exercises to figure things out. So, just to recap here, when you see green up here, this is the standard deviations. So 0 is in the middle. That means that's the average, the mean value. When you go up a standard deviation, that's going to be 34% of the actual curve, of the area under the curve. Just one standard deviation. But when you go to 2, look at the curve, it goes down, right? So at that point, if you look at the area between this, the second standard deviation, and the negative second standard deviation, that's like 95% of the probability right there, which means things outside of that are only 5%. And a lot of times 5% is a magic number used in statistics to decide if something is significant or not. If we go to the third standard deviation, from the third negative standard deviation to the positive third standard deviation, that's 99.7 of the curve. So almost everything is within the first 3 standard deviations on both sides. Those 6 standard deviations right there. Everything outside of it is only 0.15% on this side and 0.15% on that side. So that's a total of only 0.003 of the probabilities outside of those 6 standard deviations that I told you about. The 3 on this side and the 3 on that side. It makes it pretty easy when it is as the standard normal deviation. Standard normal distribution, just because you can look at it as left and right, plus and minus, and you can see the curve. And then there are ways to adjust it to your actual data if you want to look at it in terms of the actual data, which I didn't do here. But I might get more into the actual formula in another video because I think it's kind of interesting. But for now, this will suffice. Down here, it's just basically restating it. So if you're at the negative third standard deviation, you're subtracting that sigma value 3 times from you're subtracting 3 times the sigma value from the average here. And so that's what this point really is. And we'll get into some examples here in a little bit. So that's what this looks like. So just remember that the red or pink part is the actual probability area, and that the x-axis are the measurements and how extreme those measurements are. And then looking at the curve corresponding to it and looking at the area under the curve, you can decide what percentile it's in. So here it's going to be in the 95 percentile. So if there's anything greater than that, it's only going to be like a 5% chance of it being greater than the 95 percentile, right? Whereas if it's in the middle, it has a 50-50 chance of being on either side, because that's in the middle of this curve. And like I said, the first standard deviation on either side, that's 34 and 34, that's 68% of the data it should be inside of just the first standard deviation, these 2 standard deviations. Then it's only 13.5% margin there and a 13.5% margin there. So that gives you an idea of how it tapers off. One more thing, the standard deviation just happens to be at a point on this curve where it goes from going down really, really, really fast to all of a sudden tapering and starting to taper off. Meaning that values after this point, they're still decreasing, but they're not decreasing as fast, and the rate at which they're decreasing is really decreasing and keeps to the point where it's pretty much a straight line, like all the way to the Atlantic Ocean, all the way to the Pacific Ocean here, and it would just be pretty much the same value. The same probability of finding any value above this, almost. Just so you have an idea of what this looks like, because it goes on infinitely. So, moving on. how do we calculate what is this format? So this says, what's the probability of any given x value being less than or equal to the average? So what do you think the answer to that is? Well, think about it. The average is right in the middle, so it would be 50%. So there's a 50% chance of a value being on this side of 0. So we'll put the answer here, which is 0.5. How about the probability of any given x value being greater than or equal to the average? I'm sorry. Yeah, that's right. Greater than or equal to the average. Well, if it's in the middle again, just like it is with this, there's going to be a 50% chance that it's going to be on that side. So we can fill this in and say 0.5. What about being between the -1 standard deviation and the +1 standard deviation? Well, if it's 34% for the first standard deviation on either side, then it's going to be 2 times 34%, which is 68%. So the probability is 0.68. When you think about it, that's even more area than it is on either side of it. So it's really well clustered in the middle. And that's the idea behind a normal distribution, because values don't tend to deviate a lot. They deviate quite a bit within the first standard deviation, but not as much in the second, and not hardly at all in the third, and rarely ever past the third. And this can help you actually throw data points out sometimes, because if there's a data point by itself and it just happens to be a really large value, like way over there, sometimes they throw out data points because it's one isolated one. It affects the mean, it affects some of the other metrics, and it could have just been either equipment error or human error, whatever the case. That's another application using the standard normal distribution. Now let's move on to the second standard deviation on either side. So what's the probability of having something outside of this line here? So in this case, it would be, let me reread this. So x is less than, so actually what I'm asking here is, what's the area between this and this in terms of probability? Because it's got to be greater than the -2 standard distribution, and it's got to be less than the +2 standard distribution. Well, you can take 13.5 plus 34, that gives you 47.5. That's on this side, 47.5 on this side too. You multiply 47.5 times 2 and you get 95%, like I said before. So the answer to this is 0.95. How about when it's the third standard deviation? So on each side. So it's greater than -3 standard distributions, but it's less than +3 standard distributions from the average. How much area is in there probability-wise? Well, we can tack on another 2.35 times 2, which gives you 4.7. Add 4.7 to 95 that we just did for the other one, and you get 99.7. So 99.7% of that area is within the 3 and the 3. Okay? So we can write 0.997. 99.7%. How much, this one switches it up a little bit. What is the probability of having a point between the -3rd standard distribution, which would be right here, and the +2 standard distribution over here? Well, we got to add up the area again. So we know on this side, we just did this, that's 40 47.5. And then on this side, it's going to be these two added. So it's going to be, oops, hold on a second. No, it's going to be, this is 47.5. And then you add, what's 2.35? So that's 49.85. 49.85. Let's get my calculator here just so I don't make a mistake. So that's 47.5 plus 47.5 plus 2.35. So that covers 97.35 for probability between this point here and that point there. If you want to know the probability of being within that range for your values, if this information is correct, which is determined experimentally already, if you want to test somebody else's hypothesis, or you just want to know based upon somebody else's data, not test it, but you want to know based upon someone else's data what the probability is. And that's going to be 0.9735. So that shows how you can use this already. Now we're going to use a practical example, probably a popular example. A lot of people wonder about this. So there was a study done in the UK about the size of the penis, the length and the circumference of it. You can look it up if you go to PubMed. So that study said that the average male penis, where they did their research, was 13.12 centimeters. Okay, the standard deviation was 1.66 centimeters. So if we do that, if we do math on this, we want to know what the probability is of x being less than 5 centimeters. So what we want to do is use this formula here to find the z value, because what we were really using here were z values implicitly. We want to know how many standard distributions that is first. So to figure that out, we take 5 centimeters, which should be x. So 5 centimeters minus the average, which was 13.12. We get negative 8.15 because it's shorter than the average was. Then we got to divide that value, what we get there, that answer, by 1.66, which is the standard deviation. It really doesn't deviate that much. That means within the 68% area, we're only looking at less than an inch on each side, because an inch is 2.54 centimeters, right? So when we do that, we end up with negative 4.9 standard deviations. That's like way over here, because this is 3, there'd be 4, and there'd be 5. So that's way over in this side. That's extremely improbable. That's way less than 0.15. So I'll just put, since it's not even on there, let's just go less than 0.0015. And it's probably a lot less than that. Well, actually, it's probably pretty close to whatever it is at the 4th standard deviation, because it's just pretty much a straight line the whole way. So if we wanted to figure out the 4th standard deviation, we might be able to do that actually on here. If we use this app. So on this, we can go all the way back. I mean, I don't think it even goes that low. Yeah, it's less than what this says 0.02. It doesn't even go below that. So it's really, really low, extremely rare. And that's that. So how about if it's 15.88 centimeters? So you can go 15.88 minus the average, which was 13.12. Then you take and you divide that by and you got to press enter first. You divide that by the standard deviation, which is 1.66. And actually you just happen to get 1.66. So if you're to look at this, you're going, so where's 1.66? That's 1, and then 2, so it would be like somewhere like right around here. So if we use this, because I don't have a table in front of me, it's way easier to find it. You would just move this to where this yellow says 1.66. Gosh, it's touchy. So it's over 95%. So the answer would be like 0.95 something after that. Then what about 20 centimeters? Okay, well, we can do the same thing. We take 20 and subtract 13.12. We get 6.88. We divide by 1.66, which was the standard deviation. That's 4.14 standard deviations. That, again, that's like over here somewhere. So that's more than 99.7%, really close to 100% somewhere, even though there's never really 100%. So we can say that that is greater than 97, oops, wrong one. That's greater than 0.997, at least, that we can say for this. Using this, might get a more precise value. We get, because remember it's 4 point something. As far as it goes, it's 3.4. Well, this is flawed. It's not exactly correct, but it's so close to 100% that that's like extremely long. So I hope this at least was kind of interesting to you and gave you an example of how the standard normal distribution formula, or just the normal distribution in general, can be used to at least make judgments about something. In this case, if this is really important to somebody, they might just want to know how rare it is for whatever length, whether that matters or not. But that's just a way to use the normal distribution and statistics to make judgments. And the more you learn, eventually you can test hypotheses and all kinds of things when you're given statistics, and see if they even make sense. So you can even do your own tests and see if that really makes sense, or if there's some other factor, etc. Well, I hope you enjoyed this. Thank you.